Gotta get a spotter here.
One second. Hold that thought. Sorry. Good?
Well done.
Good to go, Max.
All right, cool. All right, welcome everyone. Thank you for coming out tonight. I just want to take a minute to introduce tonight's speaker, Charles Bracken. He's got books back there that he said were his pandemic project, talking about astrophotography and learning the night sky. And tonight he's going to talk to us about fun with mosaics. So without further ado.
Great. Thank you so much. Yep. Thanks, everybody, for coming out. All right, so it is a terrible night for astronomy, but a great night to talk about astronomy. So thanks, everybody, for braving the fog and the rain and everything for coming out. Tonight, I want to talk about mosaics. So this has been a couple of projects of mine recently for mosaics. So I'm going to talk a little bit about how to create mosaics. There'll be a technical aspect in the first half, and then the second half is maybe a little more fun with mosaics. We're just going to dive in and look at some of them, okay? So this is me. This is my scope down near Doylestown, Pennsylvania. I'm just across the border here in Bucks County, Pennsylvania. That's my scope in my backyard. This is, I think, you can see Venus there in the background, but that's my favorite moment, right? It's the sun is about to set. It's a clear night. Hopefully, we're going to get some good pictures that evening. I have a website, digitalstars.wordpress.com. That's where it's just a blog where I post my images on there. I've written several books. Those are actually the books that are in the back, but the Deep Sky Imaging Primer is my main book. That is basically a how-to guide. That is a textbook for astrophotography for anybody who wants to get into it. The Visible Universe is more like my coffee table book. I did that with Max Whitby. That's what I was talking about, was sort of my pandemic project. And I'll talk a little bit more about a very important mosaic in that book. I started this hobby of astrophotography in 2011, 2012, around that time in earnest. I always had Sky and Telescope and Astronomy magazine as a kid, and I used to look at the pictures in the back. Wow, I want to take pictures like that. And then you sort of look at the ads for the telescopes, and you go, ooh, I want one of those. And you look at the bottom, and you see the price, and you're like, wow, okay, I am not getting one of those as like a 12-year-old, right? But when I got my first real job, the first thing I did, I got my first bonus, and the first thing I thought of was, let me go back to that thing I wanted to do as a kid. Let me see if I can do this. And sure enough, for those of you who have tried it, with relatively modest equipment, you can take some pretty amazing pictures these days. And so I was hooked right off the bat. So we're going to talk about mosaics today and a little bit about why. I'll go into, unlike most astrophotography, mosaics require some planning and some thought into acquisition, or at least a little more than you would normally. A lot of processing. And then we're going to look at 3 really big mosaics that I've taken. This, by the way, for those who aren't aware, this is the center of the Heart Nebula, Melat 15. That's the name of the little cluster there, and you got those really cool fingers of nebulosity. Okay, so why would you subject yourself to the challenge of shooting a mosaic? Well, inevitably, you're going to start in astrophotography. You're going to start taking pictures of objects, and some of those objects you're going to find are just too big for your field of view, right? So your camera sensor might be too small, your focal length might be too long for that object. And for those of you who haven't tried astrophotography, it's surprising that the pretty images that you see are not highly magnified, right? So a lot of the deep sky objects that we take pictures of are many times bigger than the full moon. They're up there all the time, and they're just really faint. So it's not a matter of zooming in and needing a high-powered telescope to magnify in on something. It's usually a matter of just collecting a lot of photons, a lot of light, really long exposure times to reveal them. They're there, they're just very, very faint. And you may find that the object doesn't fit in your field of view. So you say, what if I took 2 pictures next to each other and stitched them together? And that's where you're getting into mosaics. So they're going to give you a wider field of view. They're going to give you better resolution because you're using a longer focal length than if you tried to use like a camera lens or something like that to take a picture. And I'll show an example of this. But they take a lot of planning, a lot of time acquiring the data, and then a lot more time processing. And processing is one of the big hurdles of astrophotography. Like, you can take the same data and give it to somebody who's really good at processing with a lot of experience, and they can bring out a lot more than a beginner can. And so mosaics just take that to the next level. So this is an object, a single object that's really big. So this is called, it's a supernova remnant in Cygnus. This is called, it's got the wonderful name, G65.3 plus 05.7, right? Really glamorous name there. Nobody's really given it a casual name. But to give you a sense of how big it is, that circle in the upper right, that's the size of the full moon. This thing is 6 or 8 degrees across. It is absolutely enormous. It is also really, really dim. So if you can think about a normal exposure you might take with a camera, let's say a daylight exposure, you're gonna have just the light flash onto that sensor for 1/250th of a second or so, right? Tiny, tiny fraction of a second you're taking that exposure. This is about 90 hours of exposure. That's how faint it is, right? So you need to leave the camera lens and the shutter open effectively for that long. And obviously, you can't, the night is shorter than 90 hours, so you take it in, short increments. So I use 5-minute exposures for this. This is hundreds and hundreds of 5-minute exposures. It also required a mosaic. So this is actually a 2x2. So it's seamlessly stitched together, so you can't tell, but this actually is so large that even my widest field of view scope, it took 4 pictures, a 2x2 mosaic, to compose this image. This is even wider. So this was my project for last summer. This is half of the Constellation Sickness. So this is a 20-panel mosaic. For those of you familiar with the night sky, you can see, right, there's the North America Nebula here, right? There's the Gulf of Mexico and Florida, right? We call this the North American Nebula. This is the Pelican. I hope you can see the Pelican. There's his eyes, there's his beak, right? This is sometimes called the Butterfly Nebula down here around the star Sauter. There is the Crescent Nebula, and actually cut off the bottom is the Tulip Nebula. And then we've got some that don't have funny names. Sharpless 119. Not exactly great name. I like to think it looks like a clam with a pearl in the middle of it, but that's just me. So this is a really wide field. This is something I can't even remember. This is like 15 degrees across or something like this. But if you were to look at the night sky, I mean, you're looking at, hold your arms out like that. It's like that big of a chunk of the sky. It's absolutely enormous. And it took 20 panels to compose this. This was all I imaged last summer. I didn't take pictures of anything else basically from May until September. Every clear night down near Doylestown, I had the scope out and was shooting this. So you can, if you want to get a wider field of view, right? You've all had a zoom lens, right? You can just zoom out, right? You use a wider field of view. And so here's one of the same objects. We just showed the North American Nebula. There's the Pelican. This was taken with a camera lens. This is a 135 millimeter lens. I love these Samyang 135s. You've got to manage focus on it, but this is a really great piece of equipment for those who want to do wide field photography. And this is a really cool image, right? This is capturing a huge nebula. It's capturing a huge chunk of the sky. But at some point, you want to get higher resolution, right? You want to try to capture that in higher resolution. So to give you a sense of the difference, let's zoom in on that. So this is called the Cygnus wall, usually. This little bit would be Mexico, I suppose, if this were North America. If we zoom in on that and look at it in this image, and then compare it with what you get from a larger scope. So on the left this is what a camera lens, and this is a very good camera lens, will give you. This, look how much sharper this is. This was taken with a proper telescope. This is a Takahashi FSQ 106. So this is a 4-inch telescope, a 4-inch lens. So you get much, much higher resolution, but this is the full field of view. This was just a tiny little speck on that other image. So the idea is, can you take this and just take lots of them and stitch them together? And then you get this really wonderful high resolution image. So let's talk a little bit about planning. So you've heard me throw around numbers like 90 hours of exposure time. Some of them will see even longer. You're committing yourself to a lot of time, so you got to plan this out. The last thing you want to do is take the wrong spot of the sky or have them not overlap the way you need. So it's going to require some planning. You also have to think about, these are multi-month projects. The images I'm going to show you all took several months to put together. And they took months of nights data to combine. So you have to be careful. Are you going to finish this before the object swings out of view, right? So if you're looking, at one of the summer constellations, you better finish this up by fall because those constellations are not visible in the night sky until next spring, right? So you have to think about that. So a little bit of planning you might not normally have to think about. You also want to plan them so that they have to overlap because they have to overlap a good bit. And I use 15 to 20% as a good benchmark here. Because in the processing, you're going to have to overlap them so that the two images can be matched so you don't see any seam. So the computer can look at the overlapped area and interpolate where it should sort of adjust each of the images so that they look like there's no seams, so that it looks flat. Okay, so let's look at how I used to do this. This is actually my notebook, and this is my first talk here. I spoke here several years ago. It was 6 or 7 years ago. It feels like, and it was the first mosaic I'd ever done. And this is my lovely notes on planning it, and you can see it started out as a I don't know. Who am I kidding? You can't see this. This is a 2x3. This is my chicken scratch handwriting. This was going to be a 2x3, but unfortunately, one of the panels, I took the camera off and I put it back on. The rotation wasn't quite the same, and here I am trying to calculate to make sure that the overlaps are going to work, but this ended up being a 6-panel mosaic. This is me more recently. This is 2021, and that lovely object we just spoke about, G65.3, and this is me sort of manually planning out a 2x2, right, and thinking about, okay, are they going to overlap? Well, everything's a lot easier as technology progresses, and so now you just open up software like Nina. Nina is free, and it will plan out your mosaic nicely for you. You tell it, oh, I want 15% overlap. I want to point it here. It will download an image of the night sky from NASA, overlay what you want. You can shift it around. And then the cool thing, if you're using Nina to control your scope, which is what I do, right? So I have Nina controlling the mount and telling it where to point and telling the camera when to take pictures every night. You just export this into a sequence, and it saves them all, and then you just start shooting, right? And then you keep shooting, and you keep shooting, and then you wait for the next clear night, and your next clear night, and then, in my case, by the end of summer, you have all the data, and then you sit down and go, man, now I got to process this thing. So let's talk about a couple quick suggestions for acquisition. You heard me talk about don't rotate your camera. The camera rotation's got to be the same. There's a couple other things you have to think about is that you want the amount of data that you capture per panel to be approximately the same. And I'll show you an example of this in a minute. But the amount of data you capture determines how noisy the image is. We call that signal-to-noise ratio. So if you look at an image, like you may have seen, if you use your camera phone, and you take a picture in the dark, and it looks all grainy and you can barely see anything, like that's a really... We say that's a noisy image, right? That means that has a low signal-to-noise ratio. Imagine trying to combine that with an image you took under bright lights, right? And then you would notice that. Like you can't overlay two panels that have different signal-to-noise ratio. So you have to think about it. Okay, did I capture 4 hours in this panel, 4 hours in this panel? Okay, 4.5 on this one. That's okay. But like they got to be fairly close. The other thing is you have to think about gradients. So this is the bugaboo of processing, especially processing mosaics, are light gradients. So around here, when we look up at the sky, you are going to have light pollution from New York, you're going to have light pollution from Philadelphia, light pollution from your neighbor, and that's creating this glow, and it's uneven around the sky. If the moon is out, and it's, let's say, partially full, it's over somewhere, and it's actually moving with the sky. So when you combine all these images together, you're going to have this complex gradient in it, and you have to subtract that out. You need to take all that out so that it's almost like your image was taken in space. So you're going to subtract all of that out. That's a lot easier if you're taking pictures from the desert, but obviously around here it's a lot harder, and this is the situation, I think, for most people. So in general, you want, if you're working on a mosaic, to take the pictures as much as you can to try to finish one panel and one channel per night so that the gradient is at least fairly consistent. That'll be easier to subtract out. If you take it on a different night, the moon might be in a different place, and that can make it a lot more difficult to subtract the gradient out. And we'll see gradients are what are going to lead to the visibility of seams in your image. So I mentioned getting the signal to noise ratio right. So this is an example. This is the Large Magellanic Cloud mosaic. So this is 27 panels. This is just H alpha data. So this is just focusing on the wavelength of light that nebula produce, right? So emission nebula emit primarily at this one wavelength of light. And we can use that to our advantage and filter out everything but that wavelength. And that allows us to block out most of the light pollution. So this is the one kind of object where we have an advantage over light pollution. So no matter how bad the light pollution is, you can cut through it for this type of object with these filters. But you can see, if I zoom in here, and you can see this panel down here had about half as much exposure time as this one up here. And you see how sort of smooth this one is, and this one's kind of noisy. Like there's no amount of processing that I'm going to be able to do that's going to effectively get rid of that. So we had to go back and make sure, okay, so we need to shoot another couple hours here. You also see some crazy little artifacts, these little pinch artifacts that happen that you have to deal with in mosaics. We don't have to go into that, but there's just a lot of complexity in taking a lot of pictures and stitching them together versus sort of trying to take one picture of one area. Okay, the technical part, for those of you who are interested, I recommend Astropixel Processor for most mosaics. It just, with the settings I'll show you, it's fairly turnkey. It can take care of most mosaic situations. You get into really big ones sometimes, or there's some different situations you might have where they have to be projected certain ways. You have to go to PixInsight. PixInsight's, for those of you who know, is a lot more complicated to use. But I will say Astropixel Processor will do a great job with darn near any mosaic you can throw at it, as long as you sort of follow the rules I'll show. You want to keep everything linear, which means don't stretch it until you've got the whole mosaic combined. You have to preserve the linearity of the data so that you can do that gradient matching. And then finally, you can integrate the color. You can combine your color channels when you want. So I know that might be Greek to some of you, but for some of you who do image processing, this is the basic guidance. Here's an example of what I just took 4 images. This was literally an evening where I kind of didn't have a plan. I thought, oh, I'll just point the scope and look at the bubble nebula and the lobster claw nebula. So just for those who, this is the bubbles in there. That's called the lobster claw. This is called the cave up here. And I just said, okay, I'm just going to take a mosaic tonight. I didn't have a plan. I just pointed it up there, took 4 quick sets of exposures. I did the light pollution subtraction tool, and then threw them into Astropixel Processor seamlessly. Like you can't tell any seams. It did a fantastic job. So for most situations, that's what I recommend. If you zoom in, add a little contrast, just gives you a sense of all the different objects. Each of these, by the way, these are emission nebulae. So this is ionized hydrogen gas out in space. So this is gas that either never coalesced into a star or is left over from a star that exploded. It's mostly hydrogen out there. And what's happening is it's getting ionized by really hot stars. So there's probably these really bright ones here are what are called O-type stars, and they are extremely hot and they emit UV light. That UV light ionizes the hydrogen, which means it strips the electrons off of it. And when those electrons recombine, it emits light similar to like a neon sign, right? A neon sign is an ionized gas, that's ionized neon. This is ionized hydrogen out in space, and it emits in this very specific color. So that's what you're seeing. So this image is in black and white, but it's filtered only to see that hydrogen gas. And you can see there's some globular clusters. This is Messier 52, and I think there's a couple little clusters scattered around there. Okay. Again, those on YouTube can screenshot this. This is the method in Astropixel Processor, right? So this is I said it's turnkey as long as you follow these instructions. These are those instructions. So I won't go through these in detail, but I just want to highlight one point. You heard me mention gradients. So what happens if you don't subtract those gradients out and you throw them into Astropixel Processor and expect it to try to form a mosaic for you? And this is what you get. This is what I was talking about. It can't, It's got a gradient of light that's sort of, light pollution on higher on one side than the other, and then you're trying to combine it with another image, and there's no way to match them effectively. So you have to get all that out before you do it. And look what happens. If you do subtract it out, that's what you get, right? One extra step, but you have to do on every single panel. Make sure you get a clean panel with the light pollution, subtract it out, and you get a really nice image. Does anybody recognize what we're looking at here? I'll help you.
Oh, Cassiopeia.
Yeah, this is Cassiopeia, right? So there's the Pac-Man nebula right there. This was, again, just a quick image, just taken. I was just literally just practicing a little bit with mosaics and seeing what I could do. And you can see, this was just quickly thrown together. There's still some residual light pollution issues, but this can be subtracted out pretty straightforwardly. If you have to go to PixInsight, it's a little more complicated, but it gives you a lot more control. So that's kind of the theme with PixInsight. Again, I'm not going to go into all the details. You can go back and look at this, look at the recorded version of this. But this is my basic workflow, and it's pretty different. You don't just get to throw the panels in, and I'll call out a couple of things here. So Blur Exterminator has come out recently. So this is the first sort of machine learning algorithm for astrophotography. It's pretty impressive. It really sharpens up your image by essentially finding the optimal solution for deconvolution for the image, which has been a notorious pain to do manually. And so it solves that for you and almost magically sharpens your image. But it has to be done at the linear stage, so before you've stretched the image. So that has to happen early on. ABE or DBE, these are PixInsight's tools for removing gradients, like we just talked about. That has to be done here. But then this very strange thing, image solver. So the way you can create a mosaic in PixInsight is that you plate solve the image, which means you ask the computer to solve exactly where in the sky it is. It solves it just to super accuracy where in the sky that is. And then it can take all your panels, because now that it knows their location in the sky, and later on, this mosaic by coordinates will then actually use that information to align the panels that way. So you first have to solve the image and then combine it there. And then you go on to process it as usual. There's a couple little nuances here, and you heard me, I keep putting my hands up like this, I find that I'm talking about these mosaic panels matching. So there's special tools we use to do that. In normal astrophotography, we'd use something like linear fit, which is where we take two images that we know over the same spot in the sky, and we say, okay, this one's slightly brighter on average. Let's bring those two back in line. It's literally like a algebra 1 level linear fit, right? Y equals mx plus b solution to bring the two images into line as far as brightness, right? Special things you have to do, and there's different tools for that. So there's frame adaptation, DNA linear fit, if there's one other I forget, but basically it's only looking at the overlapping area, because these are not two parts of the same sky. You don't expect these two panels to be of the same brightness. You only want to consider the parts that overlap. But again, you have to take the light pollution gradient out first. This, I also won't go into a lot of detail on this, but this is a complex and confusing topic. Local normalization versus global normalization. And it's important, it's not normally all that important, but remember how I mentioned that you might be taking pictures one night and the moon's here, and over the course of the night, right, you're tracking the object and the moon has moved a little bit, and now the gradient's coming from a slightly different direction. Effectively, this is an attempt to solve that and to better subtract out the gradients, because the gradient might have a complicated shape to it. So again, without going into the details, you wouldn't normally think too much about this, but when you're doing mosaics, you have to do everything you can to get those gradients out, and local normalization is the tool that you want to use that. The tool's names vary slightly depending on whether you're using Astropixel Processor or you're using PixInsight. Okay, so let's look at Cygnus. This is the mosaic I showed you earlier. Again, this is just the hydrogen, right? So we talked about ionized hydrogen out in space. This is the 20-panel result. This is uncropped. This is, after I've basically gotten everything to overlap nicely and plate solved everything, put it together, this is what comes out. So I'm like, well, that's pretty nice. I'm pretty happy with that. Give a sense of how big this is. So this is 21,700 pixels wide, right, this image. It's 17,000 pixels high. So this is a 380 megapixel image, right? So the fun thing is you can really zoom in on it and still see individual objects. This is what happens when I added the oxygen data. So I mentioned there's hydrogen gases out in space and it's ionized. There's also, a lot less of it usually, oxygen out there in space. It gets ionized as well. It emits at a different wavelength, glows sort of a greenish blue. So if you take the hydrogen data, you map it to red. You take the oxygen images. This is a whole different set of images I had to acquire. Map those to blue and green, and you get this. Now you start to see a little color variation, right? And you can see, right, so the Crescent Nebula down here, a lot more blue, right? The Butterfly Nebula here, a lot more red. This means this one's primarily hydrogen, this one's primarily oxygen. And then you can sort of see, you know, different areas of different other nebulae are more hydrogen or more oxygen. But there was a problem. I posted this image online without looking at it carefully, and somebody pointed out, hey buddy, look at the lower left corner of your image. Oh man. So this is where they didn't quite line up, so I had to go back and enable some different features in there. This took a couple hours, and for those of you who've ever futzed around with ransack tolerances and things like that, trying to get your images to solve right, you can sympathize. For the rest of you can just know that I was able to fix this. I also went out and acquired a third channel of data. So we've talked about hydrogen, we've talked about oxygen. There's also sulfur out there in the universe, and it gets ionized as well. So sulfur gas, we think of sulfur as a solid here on Earth, but molecular sulfur in space can be an ionized gas. Combine all three of those together, and this was the final result, right? So this is my summer project last year. Cropped it down. This is 320 megapixels, 20 panels. It's 1,891 3-minute sub-exposures, right? So I mentioned you take it in individual exposures. I used 3 minutes in this case. So for a total of 95 almost hours of exposure time, right? So this is a gigantic one. And we can look at it to orient you. For those of you who've seen like you're looking at a constellation map. This is what you would see on a constellation map as far as those lines. This is the brightest star up there, Deneb, and then Sauter right here in the middle. And if we zoom in on a couple of the highlights of Cygnus, right? There's some really cool objects in here. So obviously the first one, the North American Nebula, right? And you can zoom in on this mosaic and it still shows up really nicely. We've also got the boringly named Sharpless 119. I guess it's not boring if you're Stuart Sharpless, who was, the person who cataloged it. But for the rest of us, Sharpless 119. But I think it's a fantastic object. This is the one I said I think it looks like a clamshell with a pearl in the middle, maybe. Look at some of the smaller ones. So this is Sharpless 115, Sharpless 116, not very often imaged. I'm saying Sharpless all the time. Sharpless, Stuart Sharpless created one of the first catalogs of what are called H2 regions. So these areas of hydrogen gas that are out there in our galaxy that are ionized. So he created one of the first catalogs of this. There's 311 objects in it. Many of them are some of the prettiest things that we image in the night sky. This is LBN, that stands for Lens Bright Nebula 331. I think that's just really cool. Looks like a magic carpet or something, like this very cool wavy look. This one is interesting. This is Westerhout 63. This is another supernova remnant, and you can barely see it here. So what I'm looking at is just look at the blue, and you can sort of see this. Actually, it goes over here. This blue outline. It's shaped a bit like a lemon, and it's this really, really faint blue outline. I didn't even expect to pick it up in this image, but it does show up. This is an exploded star. This is a supernova, and it's heavy in oxygen, and this is the shell. You're looking at literally just the shell of expanding gas. In really long exposures, it has this really nice 3D look. You can see that it's a clear blue shell. And I would point you, for those of you who are on Astroben, somebody actually zoomed in even tighter and took a 24-panel mosaic of just this, just that little area. So it just goes to show you can mosaic anything. Here's another object. This is called the Propeller Nebula. People call it that, DWB 111. We talked about the Butterfly Nebula here. This is the Crescent Nebula. This is one of my favorites. This one is a star that's kind of in the process of exploding. I believe this is a Wolf-Rayet star. So it's sort of expelling its outer shell, and it's got this really neat ripply look to it. This is another Wolf-Rayet star, 134. I also didn't expect this one to show up as well as it did, but this neat arc is like it's basically as the outer shell, the star is exploding into space, and it's got this bow shock where it's expanding outward, but it's hitting interstellar matter and slowing down, and it forms this shock front. And then the last one in this image, this is the Tulip Nebula, Sharpless 101 down there. Another very pretty object. All right, so that's the Cygnus Mosaic that I put together. This is my summer project last year. My summer project starting last fall and going through this spring was the Large Magellanic Cloud in the southern hemisphere. So this is the final results. This one's even bigger. So this is 837 megapixels, 27 panels, 153 hours. This is like 6 weekends of my time processing it. This was a collaboration. So obviously I couldn't do this in my backyard. The Large Magellanic Cloud is only visible from the southern hemisphere. So 4 people, me, Charles Pevsner in Connecticut, Raymond Protier in France, and Max Whippy in the UK, we collaborated to split the cost of sending a scope to Chile, where there's a remote hosting facility. There are people there who sort of watch over your scope and take care of it for you. But it's all, as you can imagine, quite expensive. So we split the cost of putting a scope down there. And then we got it down there, like, what's our first project going to be? What are we going to do? I said, well, let's take a picture of the Large Magellanic Cloud and capture all the nebulae in it. So the Large Magellanic Cloud is actually a dwarf galaxy that's orbiting our own. So there are several of these. This is the biggest and brightest. But this is a galaxy that never quite formed into like the grand spiral form. It's smaller, didn't have enough mass to do that. But it's actually in orbit around our galaxy. And you can see it, with naked eye from the southern hemisphere. What you cannot see with the naked eye are all these nebulae. So this is another one where I took the hydrogen gas and I mapped it to red. I took the oxygen and I mapped it to blue. And you get this really cool look. So if we zoom in a little bit on this, this is one of the most famous nebulae in the night sky. But most of us never get to see it here in the northern hemisphere because 88% of the world's population lives in the northern hemisphere. So the lucky 12% get to see this guy. This is like their M42, right? The first thing you might take a picture of or point a telescope at. This is the Tarantula Nebula. Absolutely amazing. Just got tons of structure, really bright, just absolutely beautiful. But in the Large Magellanic Cloud, it has a bunch of really cool nebulae that you honestly don't see a lot of pictures of. So just highlighting a few of them. This one's called N185, right? So this is a guy named Heinze who put together a catalog of nebulae within this dwarf galaxy. Just a really neat object. I think there's a Hubble picture of this, but there aren't a lot of amateur images of some of these guys because they're just small and they're in the southern hemisphere. I like this one. This is DEM L72. It's the letter C. Come on. It's like, it's C for Charlie, right? So I love it. Here's another group. I mean, this just gives you a sense. So remember, you're looking at another galaxy that's orbiting our own, and you're looking at nebulae and star clusters within that galaxy. Like, that's actually what you're able to do because this galaxy is so close to us, you can see that clearly. And so, I just picked this area because it has a mix of nebulae in it, but it also has several really nice globular clusters in it as well. So it's, it's just like our galaxy, but it's just this other galaxy, and you're like looking into it, like looking into your neighbor's house or something. It's very cool. It's got, I haven't even finished sort of exploring through this, and I haven't labeled everything yet. There are hundreds of objects I'm going to have to go through and label, but the idea is to create eventually a print that has everything labeled. But what I did want to do, and what I brought here tonight for those here in person, I printed it out. So this is the first time I've done this. I found there's a print shop. It's posterprintshop.com, and they're in Utah. And I sent them this gigantic image, and I said I want it printed 4 by 4 feet. Great, I had it in like 5 days. It's absolutely amazing. This is my telescope for scale. This thing is 4 foot by 4 foot. It's actually hanging on the wall over here for anybody who wants to have a look at it. Absolutely massive, but this picture doesn't even do justice to the resolution here. So if you were to print this at 300 dots per inch, which is like the highest resolution you can possibly print at, it would actually be bigger than an 8 foot by 8 foot poster. So we have more resolution than even like we can deal with as far as printing on the image. Okay, so I said I'd go over 3 mosaics. Let's talk about the last one. How big can you go? We just keep getting bigger, right? I'm getting bigger and bigger chunks of the sky. What if you take it to the absolute limit? What if you want to take a picture of the whole night sky? You can do it, and we did it. So this was just an example of I wrote some software actually to deal with the planning of it. But this is something you can't just throw into Nina and be like, give me a plan for the whole night sky. So this required some custom software. But this is 153 panels to take the whole night sky. Now, Max Whitby and I, who did this together, and he's the co-author on the book that we use this image in, The Visible Universe, you have to think about a lot more logistics here. So think about it. Half the night sky is only visible from the southern hemisphere. So you're going to have to put a camera and a telescope, or in this case, a lens, in the southern hemisphere. And then only part of the night sky is visible in each season, right? So we see one part of the night sky in the winter, another part in the summer, another part in the spring, another part in the fall. So you're going to take at least a year to get all of it. And you have to have cameras in both hemispheres. And that's actually exactly what we did. So we ended up putting cameras in the UK, Spain, and Chile. This was done with a 35 millimeter lens. So to give you a sense of how big the night sky is, I mean, a 35 millimeter lens, that's a pretty wide field of view. It still took 153 panels. But the final result is 1.1 billion pixels, 153 panels, over 500 hours. We took 700. We only used about 500 hours of it. So processing this was an even bigger task. But the final image, I think, was very cool. We were able to use it in the book, The Visible Universe, not only just as a pretty picture, but to logically break the book down into different sections. And our idea was to sort of show you what the deep sky highlights would be for any given area of the sky. And so you can see, like, I was able to reproject this image into new projections and then label where. So again, this is Cygnus. This is what we were looking at before. Remember that cross, right? So there's actually the North American Nebula. There's Sauter. This is the Tulip Nebula. So these are all the things you were seeing in the Cygnus Mosaic, right? And this gives you a sense. So this is 1/8 of the sky, this octant. That gigantic mosaic we were looking at before that took me 20 panels to put together is just this tiny little area here. So then we took the whole sky and were able to sort of show everything in context, right? So that was the goal of that book. So this is the final image. This is what it turned out to be like. And for those of you who know the night sky a little bit, if you look carefully, and especially when you overlay the constellations to give you some orientation to what you're looking at, you can see a lot of objects that you're familiar with, right? Here's Orion. The Great Orion Nebula is right there. But also some stuff, because I overlaid hydrogen in red on top of this whole thing so you can see the positions of all the nebulae better. You know, the Lambda Orionis Nebula, something maybe it's a little fainter than most people have shot. Here's the California Nebula. Heart and Soul are up here. You can see, here's the Pleiades right there, that little blue spot right there. And you can, I don't have it zoomed in here, but you can zoom in and see the Pleiades there. This is Cygnus, North American Nebula we were just talking about before. But then you get a lot of stuff in the southern hemisphere that, like, those of us in the northern hemisphere don't get a chance to see. There's the Large Magellanic Cloud. This is the largest deep sky object that has its own catalog. This is GUM 35. This thing is just absolutely massive. The beautiful Rho Ophiuchi area, right? So actually, if I go back, that's what's on the cover, right? So this is I think this is the prettiest area in the whole night sky. It's a little bit south for us here, but you've got Reflection Nebula, you've got a cluster, you've got Emission Nebula in red, just kind of everything thrown into one part of the sky, and it just looks like paint spattered onto a canvas or something. But yes, this is the final image. I think this is as big as you can go. This is literally, there's nothing else to take a picture of. So I think I've reached the limit on mosaics. Now I got to go back to finding other things to take pictures of. So I'd be happy to take any questions. I appreciate your attention tonight. Thanks for coming in. Happy to be here. Appreciate it. Yeah.
I was just wondering, what kind of computer processor and computer system are you using? How many gigs of RAM?
Yeah.
Et cetera, memory.
Great question. Yeah. So to prepare for the big mosaic, I did upgrade. I mean,
really?
yeah, I was. I knew this was coming, and I told Max, I was like, okay. So I had 64 gigabytes of RAM, using NVMe drives to keep everything really fast. And it's just a Ryzen 7 processor, though, so it's not like an amazingly fast processor. Most of these things were just going to take overnight anyway. So there were a lot of steps along the way that it was going to be 8 to 14 hours to process. So speeding that up to 4 to 7, it's still going to be something I did overnight, so I didn't have to worry about that too much. But yeah, this was computationally intensive. Yeah.
Your night sky mosaic that you had, is that analogous to like a map of the Earth kind of laid out? You can think about it the same way.
Exactly, yes. So I didn't draw them on here because they kind of clutter it up, but it's very similar to like a Mercator projection. It's actually a slightly different one called an Equirectangular Projection, but that's exactly it. So you would have, lines of declination is north-south here, and then right ascension, lines of right ascension, and declination running left-right. So yeah, I didn't put the grid on, but that's exactly what it is. Yeah, and you can see that, right? So you see the distortion, and as you approach that's Polaris right there, right? So that's the North Star, and by the time you get up that high, it just gets stretched out, because what you're doing, you're taking something that's not that wide, and you're trying to pull it out to fit this grid. Yeah, but great question. Yeah.
That can't be all the questions.
How large is that file? The finished
That's a great question. So the full resolution version, okay, so the biggest version is the one I have in Photoshop, which actually I had to cut down because it exceeds the size Photoshop can deal with, is 16 gigabytes. So even on my computer, it takes even when I go to open it, it's like a good minute before it actually pops up on the screen. Yeah.
Did you have to stay up or wake up to move your camera?
That is another great question. Actually, we were talking about this when I came in. So, no. Thankfully, no. So software like Nina, you can get your scope set up and you get it aligned so that it says, okay, we both agree that we're pointing to this part of the sky, and you connect the camera, and I've got a little computer, very cheap little, it's literally about that big, sits on the side of the telescope, and I just connect to it from the warmth of my house, or the cold of my house, whatever it is in the summer, connect to it, and it's sitting there using the software called Nina to plan it out. So Nina will say, point the telescope here, take 36 pictures of this duration. Move the camera here, take 36 more pictures like that. So there's software that handles all that while I am sleeping away. Now, sometimes something happens, you get a wind gust and things get thrown off, or clouds roll in or something, but in general, when things go okay, I'm just sleeping. I don't have to stay up with it, thankfully. Yeah, great question. And then in Chile, obviously, I was asleep, when all that was happening, yeah. Yes?
How often do you burn through cameras or other type of equipment?
It's surprisingly resilient. I'll say, astronomy equipment is one of those things, it's great, you can buy it used and be relatively confident that it's going to last for a long time. And most of the equipment I have, I bought used on Astromart, and I sell it used on Astromart later and so the actual net cost of ownership is not that high. So the cameras have held up. I have ZWO cameras. I've never had a problem. They've held up fine. I had one mount that had issues, but yeah, really, no, it's the same equipment I've been using for years. And that's kind of the problem with astronomy as a hobby. You tend to just keep, I need the next greatest thing. And it's true, the technology does get better and you do need better stuff. So, you give yourself license to buy something new, yeah.
What was that blue star circle when you were,
The blue star circle, was it, let's see, which one? Oops. Was it... Tell me when we get to the image. Is it any of these? No? Let's see. This one right here? Or, this guy. That star has a name. That is Deneb. So you can see that with your naked eye. So this is in the summer. This is the constellation Cygnus. And you can definitely see that if you just look up, it'll be the brightest star it's actually the tail of the swan. So if you get a star map and you look for Deneb, you can see that star with your eye. Or binoculars. Even better binoculars, I recommend that.
Any other questions?
Are you interested in microscopy?
Microscopy? You know, I actually went to grad school in microbiology, so I got my microscopy out of my system. But I will say, for any of you who've seen it, there's some really cool projects you do. I haven't done this, but I really want to try it. You can take the runoff from your gutter, from your roof, and collect micrometeorites. Have you seen this? Like, it's absolutely amazing. So a certain number of dust-sized meteorites are actually falling on us all the time, and you can collect the rainwater off your roof and look at it under a microscope and find micrometeorites. I haven't tried this, but I've seen pictures of it. I really got to try it.
Magnet to go across it too.
Yeah, right. And you can pick it. So it's absolutely amazing. Like, I would never have thought that would be a thing. And really, it didn't seem like anybody was doing it until recently. But amateurs can do it. Like, you can go out and do this experiment. So, yeah, on my list is something to do. But look it up if you haven't tried it. Yeah.
Do you ever take galaxies?
Absolutely. Yes.
Okay.
Yeah.
It just, you know, I understand you did mosaics, but
Yeah.
you've been doing some galaxies.
Oh, of course. Yeah. So literally, I have a hard drive full of data from the past couple of clear weekends that we've had, and weeknights actually, that I just haven't processed yet. But I'm working on a book right now. My next project is a guide to the 1,000 top objects in the night sky. So I like to take on big projects. And I'm like 175 into it right now, so I'm thinking this is going to be a little while. But so I'm actually, I have a list of objects I am working through to take. So all the galaxies greater than 5 arc minutes I've targeted to shoot. But I've all the big ones, absolutely. So the Andromeda Galaxy, Whirlpool Galaxy, M51, I have images, all of those, yeah. And in fact, some of them are so nice you come back year after year, right? But this project has told me to stop going back to the same objects because I got to shoot all the others. Yeah.
When you were doing the work on the southern hemisphere, did
Yeah.
you ever go with the Carna galaxy?
Yeah, the Eta Carina Galaxy,
Yes.
or Nebula, yes, it was the first thing we shot. It's so obvious and bright, and it was in good position when we got the telescope. It was literally the first thing we pointed the telescope at. It is. So between that one and the Tarantula Nebula, both just absolutely stellar, and it makes you like want to go live in Australia. Yeah. Absolutely beautiful nebula. And they're so, if those of you who shot something like M42 where it's beautiful but also really bright and like very easy to get a good image right away, it's just like that. Like you take a single sub-exposure and you're like, wow, it's like just, it's revealed in all its glory right there. No processing required. Yeah. Yeah.
What's the most amount of telescopes you've had going in your backyard at night, actually collecting data?
So for a while there, and actually for one of the first images I showed you, for a while there I put 2 telescopes side by side. So I bought 2 William Optics 71s, Star 71s, and I put them on one mount, and I had this basically very similar cameras on both of them, and I was trying to get double the exposure time that way. I've never actually run like multiple mounts. I have one mount, and literally I have it, so we were talking about this before the talk. I saved my setup time. I have a pier in the backyard, but I didn't pour a concrete pier. I have two cinder blocks that are bolted together and bolted to a footer in the ground, and that's my pier in the backyard. And so I only have one pier and one mount on it to put one telescope. But for a while there, I thought I'd be clever and collect twice as much data. I put 2 telescopes on it. But the software issues of controlling 2 telescopes just became too much of a pain, and I gave up after like 9 months or something. So the answer is effectively, sadly, just 2. Although, actually, I have been running the scopes in the backyard while also it's my night to take care of the Chile scope. And so I've got one, you'll call that, it's not my backyard, but on my computer I'm running 2 at the same time.
What kind of scope is that in Chile that you have?
Oh, a Takahashi TOA 130. So it's a 1,000 millimeter scope. So really, really high resolution on everything. Yeah. All right. Well, thank you. It was so nice. Thanks for coming out, everybody. Appreciate it.
We use this piece of software, Astropixel Processor, which I keep, and
You can download